In this video, we'll talk about concavity and do example 4. So concave up. This is a picture of a function that is concave up. If the graph, one way to think about this is if the graph of the function is above all its tangent lines on an interval, then that function is concave up on that interval. You can think about it as just holding water. If it was raining, water would stay on this shape. Notice that all these slopes of these tangent lines are increasing. That is, the derivative is increasing. F prime is increasing. So for an example, maybe right here, this is a little blurry, so I'm going to just rewrite it. Here, say the derivative is -3. Be right here, the derivative is 0. And right here, the derivative is 3, positive 3. Over the interval in the domain, those slopes are increasing. You know, -3, then 0, then 3. Those slopes are increasing, so the derivative is increasing. Since the derivative is increasing, its rate of change is positive. What is the rate of change of f prime? It's f double prime. Okay? So here we are, concave up, and the second derivative is positive. Now over here we have a picture of a function that is concave down. One way to think about a function being concave down is it's below all its tangent lines. You can think about water maybe running off this shape if it was raining. All right. Notice that all these slopes are decreasing. We got a slope, say, of 3, a slope of 0, then a slope of -3. Those slopes are decreasing. Oops, there we go. Pick up the right color. So over this interval in the domain, these slopes are decreasing, so the derivative is decreasing. If the derivative is decreasing, its rate of change is negative. What is the rate of change of the first derivative? It's the second derivative. So if our function is concave down, the second derivative is negative. And we actually talked about this in a previous lesson. We noticed that if acceleration was positive, the shape of the position function was concave up. If acceleration was negative, the shape of the position function was concave down. Right? So understanding this really is our second derivative test. All it says is that if the second derivative is positive for all x on some interval of the domain, then the function is concave up over that interval. You can say on I if you want. Right, so this is, we're just using I for any interval, you know, 2 to 7 or -5 to 3 and including the endpoints, right? Just using I for any interval. If the second derivative is negative, for all x on some interval of the domain, then that function is concave down on that interval. right? So the second derivative test, or sorry, I apologize, the concavity test is used to figure out if a function is concave up or down. Sorry this was highlighted, but we can deal with that. A little bit of vocabulary of what an inflection point is. An inflection point is an ordered pair on the curve f and x comma y, and it's where that function is changing concavity, right? So if the function is continuous at that point and we are changing concavity at that point, we call that point an inflection point. Let's consider some examples. So example 4. Given the graph of h here, that's what's pictured, state the intervals where h is concave up and where h is concave down, and then state any inflection points. So here I see that I'm concave up. This is holding water. Then it looks like we're changing concavity, and now we're concave down. We're still concave down. And maybe this is a little, I'm seeing right here, it seems like it's changing right there, concave down and now concave up. And then we're still concave up. Okay, so again, stating the intervals in the domain where we are concave up and concave down, I see for x values less than 3, less than minus 3, the function is concave up, and then x values between 1 and 4 were concave up, and then 4 to infinity were concave up. I don't want to really say that you're concave up at 4. Remember, the definition of concave up is that the second derivative is positive, and the second derivative doesn't exist here because the first derivative doesn't. We can write that note, but let's put in the answer first. So h is concave up on what intervals? Minus infinity up to minus 3, as well as 1 to 4, and 4 to infinity. I'm just using my unions to include those sets all together. All right? So let's just make that note. Right, h prime of x does, or actually we can even say h prime of x does not exist at x equals 4. I'm just going to write h prime of 4 does not exist. Therefore, h double prime of 4 does not exist. Why am I mentioning this? So h prime of 4 can't, if it doesn't exist, it can't be positive. So what? So h is not concave up at x equals 4. And I'm going to do CC up for concave up right here on this little note. Okay? So bloop, right there, that little note. Now concave down, I see that my function is concave down from minus 3 to minus 1, and then minus 1 to 1. And for the same reason, we're not going to say that we're concave down right there at minus 1, because the first derivative doesn't exist, so the second derivative doesn't exist, so the second derivative can't be negative, right? Let's go ahead and write that. h is concave down on these two intervals, -3 to -1 and -1 to 1. And then the same note. But this time it's about h prime of -1. Doesn't exist. Therefore, h double prime of -1 also doesn't exist. So it can't be negative. Oops. And I just caught a typo right there. What can't be positive up there? H double prime. All right. And now inflection points for part B, right? So all this is part A. And part B, go find some inflection points. That's where they're points on the curve, they're x comma y's, where we change concavity. So right here, x is -3, y is -1 is an inflection point, and right here, x is 1 and y is 3 is an inflection point. All right, -3, -1. One, 3. Right, and I took the time to write this out to emphasize that these are x comma y coordinates, whereas up here these are intervals in the domain, right? They're describing all x values strictly less than -3, and all x values strictly between 1 and 4, and all x values strictly bigger than 4. That's what those are, right? Same thing here, intervals. Whereas here, these are coordinates x comma y. All right, and we are done.